All right, now when we're going to talk about substances in nature, we should start with talking about elements. Now, when materials, any material, is broken down by chemical means or chemical reactions into their simplest possible forms, elements are what results. Elements can't be broken down further by chemical means. They're really the simplest building blocks. Think about if you've ever built something out of Legos, right? Legos are these pretty popular blocks that sort of stick together, and you can build all sorts of neat things out of them. There's kits, so on and so forth. And that's a lot of fun for some people to do that. If you were to take the object that you build and take all the pieces apart, those fundamental building blocks are kind of like atoms. After you take it apart, you can't necessarily break it down further unless you mechanically grind it or something of the sort, right? But you get the idea. These atoms of our elements are going to be our fundamental building blocks for making other more complex substances. Just like a single Lego piece, may be able to put together to make something more complicated, okay? So now, any one particular element exists of one specific type of atom. So what do we mean by this atom concept? Well, take a look at this picture right here. This is sort of a cartoon drawing of a model for what an atom might look like on a subatomic view, okay? Look very closely at this. Study this for a second. This would be a single atom of one type of element. You see at the center of this atom, we've got these red and blue spheres. Now, in a subatomic view, these red and blue spheres are representative of subatomic particles, which are present in what's called the nucleus of the atom. The nucleus is at the center of the atom. That's oftentimes how the model works. The red spheres are representative of subatomic particles that are called protons. Protons have a positive charge associated with them. The blue spheres are known as neutrons. Neutrons have no charge, but they do have a significant mass. In fact, they're the heaviest subatomic particle. Both protons and neutrons are present in the nucleus of the atom, which is again at the center. Now, around the periphery or outside of the atom, we've got these black dots, which apparently are in motion, according to this cartoon picture. These are our electrons. Electrons are our negative charge carriers that offset the positive charges of the protons. Okay? Now, chemistry, as it turns out, is all about these electrons. The electrons can be transferred between substances, different atoms. One atom can give up electrons, another atom can gain electrons. Maybe atoms come together and share electrons in a different type of bonding. But chemistry is all about these electrons. Chemical reactions involve transfer or changes in sharing of electrons. And in a nutshell, that's what chemistry is all about. So elements of different substances, different elements will differ because they have a different number of protons in the nucleus. It turns out that the number of protons in the nucleus is what defines a particular element's identity. Elements will also have differing number of electrons. And because of that, their chemistry and chemical properties are a little bit different. Now, you may have heard of a word called isotopes before, okay? I wanted to clarify what that meant really fast before we move on. Isotopes of a given element are the same element, and that's because they have the same number of protons, or these little red spheres, in the nucleus. But two different isotopes will have differing number of neutrons in the nucleus. Now, these are those neutral particles which reside in the nucleus of atoms. Because isotopes have different number of neutrons, the mass of the atoms will differ. Okay, and that's what was one characteristic of these isotopes. But it turns out the chemical properties of two different isotopes tend not to be all that different because the same number of protons are present and the same number of electrons are present. But nonetheless, this is what we mean by isotopes. Now, in the past, you may have seen a table that looks like this. This is our periodic table of the elements. This is a list of all the elements, there's 118 on this table, that are known to mankind at present. Some of these elements may be solids in their natural state, like silicon or sulfur. Some of these elements, like hydrogen or chlorine, may be gases in their natural state. They have different physical properties. Some conduct electricity very well. Some are going to be insulators. So all these elements have different chemical properties, different physical properties. And that's because they're at their most fundamental atomic level, they're made up of differing number of protons, neutrons, and electrons. They have different parts that make it up, and this imparts them with different physical and chemical properties. But nonetheless, this periodic table of the elements is essentially a list or a chart which tells us all of the known elemental building blocks that we can make more complicated materials out of. Okay, again, there's about 118 of these. Now, some of these elements in our daily lives are far more common than others. Turns out the elements with higher atomic numbers, up close to 118, are not terribly common in our everyday life. Many of these elements have been synthesized in a laboratory by scientists, given their very difficult, complicated work. And these elements have been demonstrated to exist, but they're typically quite unstable with the higher atomic numbers. Oftentimes they undergo radioactive decay very, very quickly, even in a fraction of a second. So you might be able to confirm that you've made it, but it's not terribly significant to our everyday life if it's going to degrade so rapidly. But the lower elements are the ones that we're going to kind of be our bread and butter in this class. We're going to see those quite a lot. Those are at the top of the periodic table of the elements. But these are our building blocks, okay? Each of the elements on this table have different chemical and physical properties. Now, one more link that I want to make here before we move on. When you see pictures such as this one in your textbook, where you've got these little circles of different color, what that really means is your textbook is telling you that that's an atom of that particular element. Again, the atom being this most fundamental particle that maintains the chemical properties of that particular element. So you do see these different color spheres. We're really talking about single atoms. So if the sphere is independent and not connected to other spheres, this is what we're kind of seeing in this particular picture here, then that says we're just having one atom of that element. Now, if these spheres are connected to other elements of different in color, that basically indicates that we formed a molecule of a different compound. Okay, so keep that in mind. Oftentimes your book uses these colored spheres to help you, and I think sometimes that the exact meaning of what these pictures depict is lost. So these are elements. Now that we know about elements, let's talk for a bit about compounds. Chemical compounds consist of two or more elements that are combined or bonded together in specific whole number ratios of atoms. Now that last part is pretty important. Concentrate on that for a second and understand what it means. The atoms or the elements have to combine in specific whole number ratios of atoms, and they have to be bonded or combined together to make a compound. Some examples of compounds are shown on this slide. We've got carbon monoxide on the left, CO, carbon dioxide in the middle, and then finally the carbonate ion, CO3 2- on the far right. Now the carbonate ion is an example of a polyatomic ion. This substance is actually charged. You can see that I've got the square brackets around it with a 2- charge, indicating that that's its atomic charge. These substances are all made from carbon and oxygen combined in different whole number ratios. Carbon monoxide has the formula CO. That's got one carbon and one oxygen atom per molecule. Carbon dioxide, as the name suggests, has one carbon and two oxygens per molecule, whereas the carbonate ion is a 1:3 ratio between carbon and oxygen. Now, all three of these substances use the same exact elements to build these molecules or these compounds. But these three substances are distinctly different. They have very different chemical and physical properties. Now, both carbon monoxide and carbon dioxide are gases at room temperature and pressure. However, carbon monoxide is a very toxic gas. In fact, you usually have carbon monoxide alarms inside your house if you've got natural gas, ovens or furnaces. And that's to protect you from carbon monoxide poisoning if something goes wrong with your furnace system. On the other hand, carbon dioxide, CO2, with the extra carbon-oxygen bond, this is also a colorless gas. However, it's an air we breathe at a relatively high concentration. We also consume this gas in carbonated beverages like soda pop. It's non-toxic. So despite having the same elements that make up these two compounds, their chemistry is very different. Their physical properties are also very different. They have different boiling points and different melting points and different chemical reactivities. Carbonate ion is very different from the other two. Carbonate ion typically forms solid salts with cations or positively charged ions, like sodium carbonate. Maybe it can combine with potassium. But in these cases, materials are solid salts. There's a picture of sodium carbonate. You can see it's actually a solid white powder. It's an example of an ionic compound. In chemistry, whenever you pair up negative ions with positive ions to make salts, as they're called, this is an example of ionic compounds or ionic bonding. A salt, in general use in chemistry as a vocabulary word, it's nothing more than an ionic compound. It's a compound formed from a cation, positively charged ion, and an anion. It doesn't have to specifically be table salt. Table salt is sodium chloride, but in general vocabulary, a salt is an ionic compound. So all three of these are made of carbon and oxygen, but boy, these compounds that result have dramatically different properties. So the moral of the story here is once you start combining elements in different whole number ratios to make these different molecules or ions, the product that you produce is a new substance. It has its own properties that's wholly unique, depending upon the bonding in that particular molecule. Now, before we move on, I wanted to key in on these structures that I've drawn. Notice again, the black dots are representative of carbon. The red dots are representative of oxygen in each case. But now, instead of having the spheres touching, I've drawn in these lines. You can see in carbon monoxide there's 3 lines. In carbon dioxide there's 2 on each side of the central carbon. And then I've got either 1 or 2 on the carbonate ion. Now these lines are representative of chemical bonds. Chemical bonds are forces that hold the atoms together to make a molecule or a chemical compound. You'll see this quite a bit in this class, okay? One bond or one line is required to hold the atoms together. In these particular compounds, though, we have an example of double bonds, as they're called. That's where we have the 2 lines, and even triple bonds in the first compound, okay? So don't be surprised by that. They're just chemical bonds that hold these particular atoms together. So compounds, such as carbon monoxide, can be decomposed into their elements. In other words, we can break the chemical bond holding the atoms together, yielding carbon and oxygen atoms, or the elements that make up that compound. This is often done if we take the material under study, say carbon monoxide, and heat up the molecule in an inert environment. If you heat it up enough, you can get it to decompose. This would be called a decomposition reaction. But the important thing to realize is that that reaction yields the elements that make up the compound. And we can't break the elements down any further via chemical means. Now, on the other hand, we can do even more interesting chemistry with molecules such as carbon monoxide. Maybe we mix the carbon monoxide with other substances to drive chemical reactions to occur. And this is the realm of what chemistry is really all about. It's what happens when we combine different substances under different conditions. Can we make new and interesting molecules with interesting properties or interesting uses? So in this particular case, let's say we take the carbon monoxide and add some more oxygen. Okay, here that's shown with this red sphere to be very sort of graphical and visual. If we do that, maybe we can make some carbon dioxide. 1 carbon per 2 copies of oxygen. Okay. We might be able to react the carbon monoxide with other materials under different conditions. But you get the idea. Once we create a new substance, we can either decompose it back into elements, or we can build and make new interesting compounds. Another important consequence of the whole number ratio that atoms combine to form compounds is that the mass ratio with which elements combine for a specific chemical compound is always fixed. This is an important concept because it doesn't matter where I might purchase my carbon monoxide from, what chemical supplier, or whether I get it from Europe or Asia or Australia. If I'm talking about carbon monoxide, specifically carbon monoxide, the ratio between carbon and oxygen atoms is always fixed at 1 to 1. That's what defines the molecule carbon monoxide. Now, because of this, the mass ratio with which these two elements combine is also consistent across all samples of carbon monoxide. Not just the atomic ratio, also the mass ratio. Let's explore this further. To do this, let's look at the pictures on the left of this slide. This is what the box for the elements on the periodic table of the elements looks like for carbon and oxygen on the bottom. You see the number 6 for carbon and 8 for oxygen? That's the atomic number. That's how many protons are in a nucleus of those atoms. Now, right below the capital letter, which is the elemental symbol for carbon and oxygen, there's a number. For carbon, that number is 12.011. For oxygen, it's 15.9994. Now, these numbers will become very important to us because these are the atomic masses of these elements. It gives us some indication of what the weighted atomic mass is for these elements across all isotopes. More on that later, okay? But for right now, we can use these numbers to correspond to the mass in grams of 1 mole of this element. Now, we haven't talked about the mole concept yet, but it's going to be an amount that chemists use, kind of like a dozen eggs. For eggs are sold in dozens. Well, chemists deal with quantities of materials in moles. Well, it just so happens that these numbers in the boxes for the element correspond to the mass of 1 mole of that element. So for carbon monoxide, if I add together the numbers which are in the boxes, these molar masses, I would add 12.011 plus 15.9994. This yields 28.0104. This is the total for the compound, carbon monoxide. All I'm doing here is I'm adding up the parts. I'm summing up the parts that make up carbon monoxide. And since 1 mole of carbon monoxide consists of 1 mole of carbon atoms plus 1 mole of oxygen atoms, this mass of 28.0104 grams corresponds to the mass of 1 mole of carbon monoxide. We call that the molar mass of carbon monoxide. It's a little over 28 grams per mole for this particular substance. You're going to be computing molar masses a lot in this class, so it's a good skill to practice early on. Now, what I wanted to get back to is this mass ratio with which these elements combine. Because a little over 12 grams out of the 28 is carbon by mass, I could do the division and find that carbon monoxide is 42.88% carbon by mass. Out of 100 grams of carbon monoxide, 42.88 grams of that would be the element carbon. Alternatively, the remainder, 57.212%, is oxygen by mass. Again, if I add 100 grams of carbon monoxide, 57.12% would be oxygen. And this is fixed across all samples of carbon monoxide. Now, this is, again, important because what we're going to do really soon is learn to compute or find what's known as empirical formulas for compounds based upon mass composition data. We're actually going to be kind of working this problem in reverse. We're going to be given percent composition information and work backwards to figure out what the mole ratio is that elements combine in to form the compound of interest. The simplest whole number ratio for such a combination is going to be known as the empirical formula. We're going to work a lot of problems that deal with that, okay? But before we do that, I just wanted to introduce this concept so we can see sort of the forward-thinking problem. That's going to help when you're working the problems. Now, mixtures is the last topic that we're going to consider in this video. Mixtures are really fundamentally different than elements and compounds. And the reason why is because a mixture is going to result when 2 or more substances that are just physically combined in the same volume. These substances are physically intermingled and mixed, but the 2 or more substances, they don't chemically combine, they don't chemically react, okay? So to kind of give you a visual of what a mixture might look like, if you're not following, Think about when you go into your kitchen and you start cooking. Okay, you might get out a bowl like that's shown on the left here, and in that bowl you start adding ingredients, right? Maybe two of those ingredients, you add some flour and then you add some sugar, as is depicted here, okay? Now you can mix that up, and if you do, you've got a mixture of different granular white solids. You'd have a mixture of flour and sugar, and that's what you'd expect, right? This is an example of a mixture. Now, what's important to note here is that the sugar and the flour do not chemically combine in this bowl. They don't react. They just sit in the bowl mixed together. Okay, so this is kind of what we mean by a mixture. Another example is over on the far right. It's just some sand in water. Okay, we can mix this up, but these two materials don't react. Okay, now as a result of that, mixtures are really very different than chemical compounds and certainly elements. We don't want to confuse these topics, all right? And the reason why is because in a mixture such as these that we've had depicted on this slide, the individual components which are present really maintain their own characteristics. I mean, the sand in this water is still sand. It's going to behave like sand. The sugar in the mixing bowl is sugar. It's going to behave like sugar. It's going to taste like sugar. It hasn't changed. It's just been mixed with something else. Now, because the different particles inside these mixtures maintain their own chemical and physical characteristics, generally speaking, we can separate the different components in a mixture through physical means. An easy way to see this is to think about this sand and water. Very common, easy experiment that you may have already done, like high school chemistry, is to separate the sand from the liquid water, and maybe even throw some salt in there, because salt's soluble in the water. It's really easy to separate the sand from water. You just have to filter it with a piece of filter paper. The water passes straight through, and the sand is retained, and you get a nice, clean glass of water after you filter all the particles out of it, okay? So that's what we mean by separating mixtures by physical means. Another thing about mixtures, you can easily vary the mass mixing ratio by which you combine ingredients, or else the volume mixing ratio, okay? You think about cooking again, okay? Maybe I add 1 tablespoon of sugar, maybe I add 5 tablespoons of sugar. You can vary that mixing ratio in a mixture. You can't do that with chemical compounds. Like we learned about earlier with carbon monoxide. Carbon monoxide is always a 1-to-1 atomic ratio between carbon and oxygen. If you change that, you make something different, okay? So for carbon monoxide, that's always that 1-to-1 ratio, but mixtures are very different, okay? So you see this is fundamentally different from what we talked about earlier. Now, a little bit more about mixture terminology. Down at the bottom of this slide, you see that liquid mixtures are often called solutions if they're homogeneous, okay, if they're mixed throughout. If we've got a liquid mixture, there's a bit more terminology to know, and that's solvent and solute. A solvent is a substance that's present in the major quantity in the mixture. It determines the phase, whether it's a liquid or a solid, so on and so forth. And then the solute is the substance in minor quantity. So think about a mental experiment where you throw some salt into water. Water is the solvent. It's going to be present in the largest quantity. It determines the phase. The resultant mixture is going to be liquid. The solute is the salt, because you put that into the water. It's in minor quantity, and it dissolves, okay? So that's what we mean by solvent and solute, if you ever see those words. Now, one more piece of vocabulary I figured I'd throw in real fast here, okay? There's even solid solutions or mixtures, okay? And oftentimes you hear this word alloy thrown around, like brass, for instance, is an alloy. What that means is the mixture of 2 or more metals. Brass, for instance, is an alloy or a mixture of copper and zinc. It's mixed together to make a metal of unique characteristics, right? So this is what we mean by mixtures. It's very different than a chemical compound. All right, so before we conclude, let's just try a couple quick exercises to make sure that we have a pretty good idea of what we've learned. This is actually a picture from your textbook that I've adapted for this slide. And it's pretty simple that what we're going to do here. We're just basically going to consider each picture and understand what exactly is going on here. Do we have an element? Do we have a compound? Do we have a mixture? All right, and understand why that is. Yeah, it's important. Your book likes to show these little pictures to show that you understand the concepts that are at play here. So let's consider the one on the far left. It's labeled A, okay? You see in this volume, you've got these series of these pink spheres. Looks like they're not bonded to anything, and they're all the same color. Those are hints that what we're dealing with here is probably a collection of gas phase atoms of a particular element. There's only one color sphere, and that gives you a hint that we're dealing with atoms of a singular element. Moving over to the next one in B. Here we've got yellow spheres. Okay, now if we look very closely, these yellow spheres are a little bit different than what we had in A, because for every fundamental particle that's present inside the volume, you see that you've actually got two of these spheres that are connected together. Now they are the same color, but there's always two connected together. So when I see this, I think of compounds like hydrogen, H2, nitrogen, N2, oxygen, O2, iodine, fluorine. All of these are so-called diatomic elements, where in their natural state, they exist as molecules of two atoms. Hence the name, diatomic. I got that because the spheres are the same color. They're all yellow, which means that they must be the same element, just bonded together. So these are, molecules of a particular element, basically. Moving on to C, the third one. This one's very different because for the first time we see two different colored spheres in our volume. We have the black spheres, which are central atoms. They're at the middle of the molecule. And then on the periphery, we've got three of these smaller blue spheres. Now we see every particle inside this volume always has one black sphere, three blue spheres. They're all identical particles. This tells me that we're probably dealing with molecules of a compound. The fact that we have two different colors indicates the presence of two elements. And because the elements always combine in a 3-to-1 ratio in the molecules, I know that I've got a compound, a pure compound. This would be representative of, if the colors were correct, of something like ammonia, NH3. Right, where there's one element that would be black in ammonia and the blue would be the hydrogen. So now those are not typical colors for that particular substance in such depictions. However, this is definitely a compound. Now the last one on the far right, what do we have going on here? If I look carefully at that volume, I've got some yellow, I've got some pink, and I've got some of the molecules that we've just talked about, all in the same volume. Wow, this is kind of complicated, right? This particular depiction illustrates a mixture. Now, how did I know that? Well, because all I've got in here is three different substances that are all mixed together. They don't appear to be chemically reacting or chemically changing. They're just physically mixed together. The three materials are different substances. They would have different properties, and we could probably separate them from one another if we tried hard enough through physical means. But in part D, this is a good picture of a mixture. Alright, so I've got one more fun exercise here to tie things together from this lesson. This exercise is to write formulas for each compound that is depicted on this slide. Glucose is on the left, and a different compound called ethane is on the right. I want you to write the chemical formula for this and rationalize that in your head, just so you can see how the atoms are coming together to form more complicated molecules or chemical compounds. Let's start with glucose first, on the left. To write the chemical formula, we proceed by noting which elements are present in the molecule. Glucose has carbon atoms, oxygen atoms, and hydrogen atoms. Three different elements. We'll start with carbon. The elemental symbol for carbon, of course, is capital C. So we write that first. And we proceed by counting the number of copies of carbon atoms present in one molecule as drawn. Remember, the lines represent single chemical bonds. Those are those forces that hold the atoms together. We'll learn more about chemical bonds later, but for now, they just hold the atom or the molecule together. Now, if I count the number of carbon atoms, you'll see I have 1, 2, 3, 4, 5, 6 copies of carbon atoms present in one glucose molecule. So I write capital C with the subscript 6 to indicate 6 carbon atoms per molecule. Next, I write H, capital H, for hydrogen, and repeat the process of counting how many hydrogens are present. If you look closely, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogen atoms present in a molecule of glucose. And last, I repeat this process for oxygen, the last element. For oxygen, I have 1, 2, 3, 4, 5, 6 oxygen atoms per molecule. And because of this, the formula for glucose is C6H12O6. Moving to the right-hand side of the screen, this molecule is ethane. It's a small hydrocarbon. It could be used as a fuel. If I look at this molecule as depicted, it's a sort of a space-filling model of these spheres that show the different atoms. So it's a little bit different in terms of its representation than the glucose. But in this particular scheme, the red spheres are meant to be carbon atoms, and the blue spheres are meant to be hydrogen. Now, this is not a standard color scheme. Your book doesn't use this color scheme, but it's only for this particular figure where the red is carbon and the blue is hydrogen. But from the information presented, we can write the formula for ethane molecules then. You see that you've got 2 of the spheres for carbon, so we would have capital C2, and we've got, 6 of the blue spheres for hydrogens, so the formula for ethane is C2H6. It's as simple as that.